chaos theory in action, the emergence of the butterfly. James Gleick's book, Chaos, The Making of a New Science, caught the public's attention when it came out in the mid-1980s and associated a pattern that looks like a butterfly and butterfly wings with its underlying theory of strange attractors that cause unexpected deviations in phenomena like the weather or the economy. So the butterfly effect is a term associated with chaos theory. And if you've seen the 1993 movie Jurassic Park, in it you heard Dr. Ian Malcolm, played by Jeff Goldblum, explain chaos theory to Dr. Ellie Sattler, played by Laura Dern, specifically referencing the butterfly effect by stating it simply deals with unpredictability in complex systems. And what are attractors? They are points in phase space that trajectories of some systems revolve around. What I want to summarize in this video is a range of topics that utilize chaos theory, and I'll begin with some useful definitions. Chaos theory deals with the big challenge facing researchers of any system. How do they predict what might happen given the starting conditions? The mathematics of probability is used to deal with this variation of system output given its input conditions. And there are two sources of variation and variability. One is the system itself. Is it deterministic or non-deterministic? And the second is the sensitivity of the output to small variations or uncertainties in the input variables. Input variables are called exogenous or independent variables. Output variables are called dependent or endogenous variables. Now, a deterministic system is one whose equations will give the same output every time it gets the same input. Here's an example. Dropping a ball from the same place at the top of a tower. A non-deterministic system is one whose equations might give a different output for the same input. And here are some examples. Today's stock market or weather, if the inputs are the same as on the previous state. Now let's define chaos. It is complete disorder and confusion. As used in physics, it is behavior so unpredictable as to appear random because of the system has great chaos or it has great sensitivity to small changes in conditions. And chaos theory is an interdisciplinary area of scientific study. It is a new branch of mathematics focused on underlying patterns and deterministic or non-deterministic laws of dynamical systems that are highly sensitive to initial conditions. These systems were once thought to have completely random states of disorder and irregularity. Now here are some fields that apply deterministic chaos theory: meteorology and fluid flow. Both are governed by the Navier-Stokes equations. Thermonuclear reactor design for harnessing the power of fusion. And another is the evolution of the universe. And here are some examples for non-deterministic chaos theory, economics, animal migration patterns, human behavior such as divorce or suicide, international politics and war, or the emergence of consciousness and a God. The meteorologist Edward Lorenz is considered the inventor of chaos theory. In the 1960s, he developed weather chaos theory, and he could produce ensemble or a collection of weather forecasts by plugging small input variable variations into a set of deterministic differential equations to describe atmospheric fluid flow. And as I already mentioned, plasma physicists use chaos theory to extend the fluid flow equations into the realms of cosmology and quantum mechanics to predict the flow of matter and energy. Today, they are using it to develop fusion reactors and explain the evolution of the universe. And quantum biologists are using chaos theory to explain how different species evolve or behave. How do scientists come up with their chaos theory equations? Well, by extending Boltzmann's equations and then looking for symmetric beauty in equations while inventing independent and endogenous variables that govern the output of the variables, and then experimenting via thought and using probability and statistics to test their validity. How is chaos measured? Well, by calculating a quantity called entropy, which is a term from thermodynamics that measures the random disorder at the molecular level. 19th century physicists discovered how to link changes in entropy to the flow of heat and energy, and they show that entropy in a closed system always increases unless work is done in a manner that brings order. Here's a great example: condensing a gas to a liquid. And 20th century physicists have theories that say the entropy in the universe is always increasing, which means if we decrease the entropy in some system, the entropy increases somewhere else. So, chaos, entropy, energy, and the direction taken by thermodynamic reactions, well, all of this is linked. And that means the direction of reactions in all living organisms can be determined because living organisms are biochemical reactions. But the outcomes are uncertain because of chaos theory. There's more I could say, but I'll save it for another podcast to keep this one short enough for your liking. And if you've listened this far, you now know more than enough about chaos theory to follow much of what you might read or hear elsewhere. So I thank you for listening and say bye-bye for now.